Okay, so general chemistry. You learned nitric acid dissociates pretty much 100% because it's a strong acid. All right, if you start off with a solution that's 0.01 molar nitric acid, well, that means you're going to get 0.01 molar H plus, right? Because there's a one-to-one relationship here. Take negative the log of that number, and you get a pH of 2, all right? And that's great, works perfectly. Now, what if you have a situation where you have a nitric acid concentration of 1.0 times 10 to the negative 8th. All right, nitric acid still dissociates pretty much 100%. If we want to find the pH of this, take pH equals negative the log of 1.0 times 10 to the negative 8, and we get pH of 8. All right, so what's wrong with this picture? This is a strong acid. I've added a strong acid to neutral water. Neutral water has a pH of 7. When I add a strong acid, I expect the pH to go down, right? But instead, I got a pH of 8. So this doesn't make any sense, all right? There's something obviously wrong here. And what's wrong here is that we failed to take into account the contribution of the ionization of water, right? Water dissociates into H plus and OH minus ions. When the concentration of the nitric acid is relatively high, like it was up here with the 0.01 molar, then this really becomes unimportant, right? Because in pure water, the concentration of H plus is 1 times 10 to the negative 7th. If we're dumping in a whole bunch of extra H plus, we're essentially shifting the reaction that way. And so the H plus coming from the pure water is even lower than 1 times 10 to the negative 7th. So when you're dealing with relatively high concentrations of acid, concentrations that are above 1 times 10 to the negative 6 molar of acid, then the H plus that's being contributed by water is not significant, and we can ignore it, just like we were ignoring it all through general chemistry. But if you have a situation where the concentration of acid is somewhere in the neighborhood of 1 times 10 to the negative 6 to 1 times 10 to the negative 9th, well, now the contribution of that water is really important, all right? It's important to take into account the H plus coming from the water and also the H plus coming from the nitric acid, all right? What if your concentration of acid is even lower than that? All right, if your concentration of acid is even lower than that, like say 1 times 10 to the negative 10th, then this amount of added acid is actually totally unimportant compared to the H plus. All right, so if your concentration of acid is even lower, then H plus from the acid is not significant. All right, and the only significant source of H plus is going to be from the ionization of water. In this situation, you're going to have a pH of 7, okay? But in these in-between cases, you have to take into account H plus from the water and from the acid, all right? And the best way to do this is through using systematic treatment. So systematic treatment, we have to write all the reactions that are happening. I've got the ionization of water, and I also have this dissociation for the nitric acid. Notice I wrote one arrow, right, because this goes pretty much 100%. I can write a charge balance for this situation. My charge balance is going to be H plus is going to equal the OH minus plus the nitric acid. The only thing I can write for a mass balance here is I know that the concentration of nitrate is going to have to equal 1.0 times 10 to the negative 8th, right? Because for every 1 mole of nitric acid I put in, I get 1 mole of nitrate. So if I'm putting in 1.0 times 10 to the negative 8th, I'm getting 1.0 times 10 to the negative 8th nitrate. I can't set that equal to the H plus because I have two different sources of the H plus. All right, so I cannot set those two equal. I can also write an equilibrium expression for everything that's in equilibrium. The only thing to write there is the Kw for the water. All right, and we know that's equal to 1.0 times 10 to the negative 14th. This goes to completion, so we don't write an equilibrium expression for it. All right, so now to solve this, what I'm going to do is I'm going to rearrange. Well, first of all, what I'm going to do is I'm going to substitute that value in for the nitrate in my charge balance. All right, so my charge balance can be rewritten as OH minus plus the concentration of nitrate. All right, and then I'm going to rearrange my OH minus. I'm going to rearrange my charge balance to get OH minus by itself. And the reason I'm going to do this is what I'm trying to do is get Kw, all right, in terms of only one variable. So right now there's two unknowns in Kw I can't solve here. I want to get a situation where I only have one unknown in Kw, and I've chosen the H plus to be the unknown I'm trying to solve for. And the reason I'm doing that is because I'm trying to find pH. And so it makes sense to find hydrogen ion concentration. So I'm going to rearrange this charge balance to get the OH minus by itself. And once I do that, then I can take this and I can substitute it into the Kw, all right, for OH minus. So now my Kw looks like this. Minus 1.0 times 10 to the negative 8th. Okay, so this is great. Now I have one equation and one unknown, right? Because Kw is not unknown. We know that. So the only unknown here is the H. I'm going to replace the H with X's just to make things a little bit easier. All right, so when I rewrite this, I'm going to multiply this through. I'm going to have X squared minus 1.0 times 10 to the negative X equals 1.0 times 10 to the negative 14th. All right, rearrange this again. 8x minus 1.0 times 10 to the negative 14th. All right, and you guys should recognize this as the general form of the quadratic equation, right? The quadratic equation says ax squared plus bx plus c equals 0. So in this case, my a is 1, right? That over here, a equals 1. My b equals negative 1.0 times, 10 to the negative 8th. And my c equals negative 1.0 times 10 to the negative 14th. All right? So now we have one equation, one unknown. It's the general form of the quadratic. All we need to do is solve. And I'm going to move over to another piece of paper for that. So the way the quadratic equation works, x equals negative b plus or minus the square root of b squared minus 4ac over 2a. So negative b is 1.0 times 10 to the negative 8 plus or minus b squared is 1.0 times 10 to the negative 16. And then 2ac ends up being 4 times 10 to the negative 14th. And you should try these on your own also and make sure that you can get all the numbers that I get, okay? It's all over 2a, which is 2 times 1. So then I got 1.0 times 10 to the negative 8 plus or minus the square root of, x equals 1.0 times 10 to the negative 8 plus or minus, I already took the square root, 2.0 times 10 to the negative 7th over 2. So the quadratic equation always yields two answers, right? Because of the plus or the minus. But generally, always in chemistry, there's only going to be one of these that makes chemical sense. So if we use the subtraction here, we would get a negative number for hydrogen ion concentration And that doesn't make any sense, right? You can never have less than 0 hydrogen ions. So the hydrogen ion concentration is going to have to be positive. So we can drop that negative sign. And I got X is equal to 1.05 times 10 to the negative 7th. Right? And if I take negative log of that answer, I got a pH equal to 6.98. All right, that's a pretty small difference from the pure water, which is a pH of 7, right? But that's what we expect. We added a very small concentration of acid. That acid is going to lower the pH, but it's not going to lower it very much. So this is a very reasonable answer.